Okay, today we're going to do our session on unsupervised methods. So in particular, we'll look at principal components, k-means clustering, and hierarchical clustering. So these are all pretty straightforward methods, and we'll just demonstrate on a simple example so you get the gist of it. So we're in R Markdown again in R Studio, and here we're going to start off with principal components, and we'll use a data set that's in R called the USA arrests data. And let's just have a look at it. The dim names, we see each row is a state, and there's 50 states listed, and each column is a crime category. So there's murder, assault, and then we've also got urban population percentage and rape. So we're going to do principal components of those. Let's first just have a look at the data. We look at the means and the variances of the variables. So the means are quite different, and the variances are very different. Now, principal components is about variance, and so the mean shouldn't play a role. But the variances of the individual variables will play a role. After all, we're looking for a linear combination that the largest principal component is a linear combination that maximizes the variance. And if you've got a single variable that dominates with respect to variance, like assault here, it'll pretty much eat up the first principal component, and so you won't get anything meaningful out of the data. And these variances are largely due to the fact that there's different units. Each of the variables is measured in different units. So all that's to say, we're going to standardize the variables before we do principal components. We standardize them all to have unit variance. So PRComp will actually do that for you if you set scale equals true. And so here we make a call to PRComp and assign the result to PCA.out. And then we can just print it as usual. And we see a summary. The standard deviations are actually the standard deviations of the 4 principal components. There's 4 variables, so we can find 4 uncorrelated principal components. And these standard deviations are always decreasing. So you can see them, the largest is 1.57, then it drops to 0.99, the smallest is 0.41. And then what's called the rotation are the loadings. So the first principal component is pretty much loaded equally on the 3 crimes, and it's got a lower loading on urban population. So it seems like the first principal component is just a measure of how much crime there is. It's just essentially an average of the 3 crimes. Now, notice the signs are all negative. Well, the principal components don't care about signs, because the variance of a negative variable is the same as if you multiply it by -1. The variance doesn't change. So we can easily just flip these signs and we get the same principal component, just the signs changed. And then you notice the second principal component is more heavily loaded on whether the state has a high urban population or not. So it seems like the first 2 principal components, so one is to do with the total amount of crime and the other is to do with the urban population. So that's what happens when we print. Of course, you can do help on PRComp, we're used to that by now, and find out more about exactly what it's given you and what the components on the object. But there's a very useful way of looking at principal components, and that's a biplot. And so here we do a biplot, and we notice that the fonts are a little bit big. So what I'm immediately going to do is change a font here and make it a little bit smaller. I use the CEX command, and I'll make it 0.7. Let's make it 0.6. And there we can see things a little bit more clearly. So it's made a plot of the first 2 principal components. And so since the observations are the states, we see a position for each of the states in this plot, where the actual name of the state is written out. And then in red, we see superimposed on this plot the directions of the loadings for the principal components themselves, the direction vectors. And so here we see that this first axis is largely due to the 3 types of crime: murder, assault, and rape, right? And so here's the one direction, So remember the component was negative. It had negative loadings. And so negative scores mean negative times negative is positive. So these are the states in this end that have got overall high crime. So we see Florida over there, Nevada, California, Michigan, New Mexico. And then the other end of the scale are the states with low total crime. So Maine, North Dakota, New Hampshire. So this first axis is really to do with the amount of crime in the state. And then the second axis we saw was mostly loaded with, the loading was mostly urban population. And so this axis is really about whether the state has got a large urban population or not. And that also had a negative loading. So New Jersey has got a high urban population. Arkansas is on the lower side. Mississippi, North Carolina, much lower. Okay, so one plot, and you get to see a nice summary of the principal components. So this is called a biplot. The word bi meaning both the loadings and the principal component scores are put in one plot. Okay, so principal components, very popular. I encourage you to learn more about them, use them, and incorporate them in your data analysis.